So multimodal representations. This is the lecture where we're bringing together different modalities, language, vision, acoustic, but also other of these modalities. We will study today one of the focus on this, which is multimodal fusion, bringing representation from different modalities together. And so as at a high level, because we've done so much unimodal, maybe you forgot what multimodal is about. So multimodal, language, vision, acoustic as example of modalities where you're bringing the information together. As you remember, we are using this abstract representation of modalities on purpose, okay? And so all the slides moving forward, we don't put words or frames or objects. But for now, let's say you can imagine for now that language could be words, and the blue could be the objects in the image, and the acoustic frames, that's what it could be, just to give you an idea of what they are. And then from there, you want to learn multimodal representation. That's one possibility. Or possibly even you want to be able to predict output label, or maybe even translate to another modality. And what I would present today is not specific to like, is it supervised learning? Is it unsupervised learning? Is it like self-supervised learning or reinforcement learning? A lot of the building block of multimodal are applicable to any of those learning scenarios. So I don't want to just say, hey, this is only applicable for one, but if it's easier for you, think about it as a supervised learning case. Supervised learning case, what it means is that I have a label, I have some input, and I'm going to learn a representation in such a way that I can make my prediction. This would be a simpler supervised learning way. Okay. Okay, is there a chance to? Yeah, okay. Okay, we'll continue. Okay, representation. So that's the core challenge. Representation is about learning representation that reflects cross-modal interaction. And that's where we will spend most of our time today is it, oh. It's coming back. Okay. That's where we're gonna, okay. You can see the slides on the internet also. Okay, thank you. So the important part are cross-modal interactions. And that's where we will spend most of our time is how are modality reacting or acting or interacting together. And the representation is a building block from all multimodal problems. In fact, when we thought about this course and like how to structure the course, the challenge for us was multimodal as a whole is very complex. How can we scaffold this problem? And this is why when we thought about representation as a challenge, we were like, okay, multimodal, each modality has a lot of structure, like a sentence has a chain of structure. And also sometimes the structure has like hidden structure, like a sentence has like a grammar that's hidden, but that's still part of it. But now I'm going to try to simplify the problem for today and for Tuesday. So for today and Tuesday, we're going to simplify the problem. And right now, we will only think about, I have one element from one modality and one element from another modality. So I have a word and I have images, let's say for now. Really, like, let's start simple. But even the simple is going to be hard. And by understanding that building block, that basic building block, then it will allow us to go to more and more complex. So why would you have this only two elements? It may be that you have a sentence, but you're really just looking locally at doing multimodal representation. Or sometimes modalities just don't have the structure. And so some modality may have only one element, or some modalities may in fact be able to summarize easily into one vector or one representation. So let's start with this simpler problem for now. And the three challenges we identified for representation were fusion, coordination, and fission. Fusion is the idea that the number, what really differentiates all three of them is the ratio of input and output. So the input in fusion, the number of input modality is larger than the number of output representation. So you're really trying to condense, to integrate, to fuse the information. The coordination, which has become, I will say, almost a de facto when we think of like architecture, like transformers. Now coordination and contextualization has become a very important aspect of our way of learning representation. And there, if you have two modalities, your goal is no more to fuse, but to contextualize, to coordinate, to exchange information between modalities. And this one, we debated long on how we will call it. Fission just sounds good, but the concept here is to factorize the problem. What are the factors that are involved? So you could say, take the fusion, but in a way, the fusion, break it in pieces, break it in factors, saying, hey, the way my modalities are interacting with each other, the way that modalities are interacting with each other, it may be more than one way. Maybe language and vision, there's more than like, so we talk about language and vision because sometimes you have a word and it corresponds to the object. It's exactly a correspondence. But sometimes maybe there is a word that is kind of a relationship, like father of, or parent of, or like there's a relationship. So there may be more than one way these two are interacting with each other. And I want to be able to model all of these different ways. So fission is in that sense. So today we're going to focus on fusion, which is really the bread and butter of multimodal for a while. And the core, when we do the fusion, the important thing is we will want to model how modalities are interacting with each other. That's okay. That's getting okay, good. Don't step here. I don't know. Okay, cross-modal interaction. Sorry, today is an interesting day. So the big revelation we had while writing the survey paper, and really we were kept asking ourselves, our cross-modal interaction, something, if you have two modalities just by themselves, language and vision, and you don't do anything about them, like perceive them or recognize or do integration, if they're not interacting in any way, there is not going to be cross-modal interaction. Cross-modal interaction only happens if you integrate, if you get a model that brings this information together. This is different. We'll talk about it later, is connection, is two objects, like the word father and the image of a father. Even if you don't integrate it, there's still, this is the same object. But the aspect of interaction only happens when there is an inference. So the inference could be because, and that's what we're doing today, it could be because we're doing fusion. It could be because we are bringing together two elements and we're trying to learn a representation. Or it could be because we're trying to do prediction. We're bringing two elements together because we're trying to predict some task or some labels. Or it could be even for multimodal translation. I'm going to be bringing two elements together in such a way that I'm predicting another modality. For any of those, I'm using the term inference. For you could write it the word model. for any kind of model or inference that brings these two modalities, this is when cross-modal interaction happen. And so you have to ask yourself, what are the different ways modalities can interact with each other? And I gave you a glimpse at it in the first lecture. What are the different ways modalities can interact with each other? With an example. So I said, is this living room? Is this a living room? And you have two modalities, the image and text. And so in this case, yes, if you look at this because of a couch, you will say there's a good chance it's a living room. But if you look at the text itself, it is ambiguous because usually laptop is not necessarily in the living room, although these days probably more than ever. But back in the days, you have an office and you have this. And so maybe it's in the study room. So there's ambiguity here. And so from a unimodal perspective, what's interesting here, and that's one taxonomy you can think of, is say, hey, do each modality bring extra information? Are they bringing the same information? Like, are they redundant or not? And in this case, there's non-redundancy. At least they seem to give us different information. But then when you merge them together, there's one modality in this case, just because it's the couch, there's one modality that is dominating the other. And in this case, there is one modality that dominates the other. And what is happening here, it's a taxonomy that is based on the response, okay? And why do I'm presenting this taxonomy? Is because that taxonomy was created not for us AI computer scientists. It was based on analyzing human and animals. It was really cool. And there, what they did is they said, how do human and animals are doing multimodal integration? They call it multisensory integration, but it's multimodal integration. And they are not computer scientists, and they're not cognitive scientists. Like they didn't go and check like within the brain how are the integration happening. They're not yet going inside it. They will look at it from a black box perspective. There is this black box, which is a human or an animal, and I give it two signals, and I look at the response of that animal. Or I give two signals, look at the response of the human. So it's kind of an interesting way. So it's the black box way of studying multimodal integration. And what taxonomy they got was, hey, at first, let's look if both modalities are redundant or not. And if they are redundant, then they propose two ways of studying multimodal. One is when both modalities, they both output the same, but if you bring them together, you just get exactly what you got from any of them. So there's no extra information. It's like they're like there's no extra information. If you were probably to do it in information theory perspective, like what you get from one modality is overlapping completely with the other modality. But then sometimes you have enhancement. So there's something more, like you get more by having both of them. They're reinforcing each other. That's the enhancement. But then sometimes you have two outputs. Each of them are giving you something different. Like if you were to just look one modality, put it through your black box, an animal or a human, and see the response. And there, sometimes you get two different response, but if you put them together, you end up getting both of them. What does it mean? It probably means, in information theory perspective, that they're just like, there's no joint information. Okay? There's probably no joint information there. They're independent. Dominance is interesting. That's the example I showed you earlier, where one modality completely takes over the other. The most, I will say, challenging computationally is the modulation one. We call it transference or co-learning. Like one modality changes the output of the other modality. That's really interesting. So one modality changes the other. And the Holy Grail, the emergence. Something completely different comes out. That's the Holy Grail of any multimodal researchers. Like put two modalities together and something come out and wow, this is different than any. There's really like something in the middle that was really like by interacting together, these two modalities were together. Now, you can see this is a discrete taxonomy. In reality, it's never going to be black or white, like one A or B. It's often going to be a little bit of everything. So maybe there's a little bit of dominance of one modality, but not complete domination. Or you will have a little bit of modulation of one modality over the other. Yeah. So what's not shown here, so the dominance, it doesn't change itself. So one modality takes over, but it doesn't, the output of modality A, let's say modality A is the dominant one. If you were to just put modality A through your black box, like a human or a cat, and get the output, like you will get the same, this is the same one. The modulation means that one modality is going to change. So this one will not be the same output. There's something that will change about it. Here it's just shown as it gets bigger, but in reality, with our dense representation, is that the representation is going to change. Yeah, but and it's rarely just one or the other, and that's why often you will have one modality dominate and get modulated. That's the kind of thing that you will often see. So modulation. I'm going to show one later, but maybe this is a sick movie. This movie is sick. The meaning of sick is ambiguous by itself, but this movie is sick. I'm telling you, this is sick. This is disgusting. Like so the facial expression modulates or changes the meaning of the other modality. So that's a modulation. There's a transfer of it. Modulation and fusion it's not like in a sense they're fusing together to get the meaning, but conceptually it's really the word that its meaning gets changed by the other modality. So you could see it as a fusion, and let's not argue, oh, it's a modulation, not a fusion. At the end, fusion integrates all of the above. Yeah. Sometimes one modality is redundant with. Oh yeah. Yeah, yes. Again, interaction only happens when there's an inference. And that inference usually has a goal or a task or a label. And so usually the interaction has a goal like that of why are you fusing that information? And that's usually that goal will be integrated in the inference, exactly. So this taxonomy that I shared is very response-oriented. It's really looking like, forget what happens inside and just look at the output. And it's a good approach. And you could also just look at the input, like which modality I put in. What we're really going to look at today is try to understand that black box, like what are the kind of interactions that could happen. And there we're really hypothesizing, because unless we go cognitive science and like really study the brain of how multisensory, and there's some really interesting research on multisensory integration. I was tempted to put a full lecture on it. It's not going to happen this year, but it's a really interesting topic of how the brain is doing it. For now, we'll do it with our AI statistician kind of brain and try to hypothesize ways things could interact. And it's impossible to think about this response and all this without thinking of context. Because remember, right now we're only looking at two elements, but each modality has a lot more elements in it, like a sentence, like all object in it. So there's a lot more. There's the task relevance as was mentioned. So we're 30 minutes in. And one thing we will discuss in later part, like next week, is like you may decide that ahead of time before doing any kind of inference that only certain elements will interact with each other, or you're going to filter or connect only certain elements. So there's this idea that there's a possibility of connecting only certain elements with others. So this is the challenge of connection. But today we will really focus on interactions themselves and how do we do the interactions. Next week, we will discuss also the connection as well. So representation fusion. So representation fusion is to learn this joint representation that model the cross-modal interaction between it. And there's really a spectrum of approaches. I mean, to say that there's only one fusion, even two, there's really a spectrum how do we quantify the exact name? Don't get over like exactly the naming we gave it, but there's this basic fusion where each modality is a little bit more homogeneous. Like maybe they're already two vectors and I can work with those two vectors and I need to find a way to do the fusion versus what we will call more like raw modality fusion, where you really have the heterogeneous raw data and you're trying to do very, very early fusion at the very early stages. So a lot of the lecture today will be kind of in this spectrum because that part of the spectrum has not been explored as much. And so there's a lot of great, if you ask me like one thing for your research project that would be interesting, try to think of very early fusion way of studying, because right now the almost ubiquitous approach for multimodal fusion is almost always with unimodal encoders. So you do have very heterogeneous modalities, but what people will do is that they will have a unimodal encoder, sometimes even pre-trained on that modality, that will give you two representations and then do the fusion. And so a lot of the approach and a lot of this lecture today will be on that kind of fusion, mostly because I also want to teach you the basic building block, because although it's simpler, it's still, there's a lot of interesting theory to have on just that part. But in a sense, it's a little bit cheating because you're not going like completely early fusion, like early stages. And so to just give an example, like you have an image and you have a word like happiness. And so often what people will do is, although these two are very different, this is a token with characters in it, you have an image with different pixels in it. And so really what the people will do is use some CNN or visual transformer to just represent the image in a vector, maybe 300 size vector. And similarly for the language with word2vec, which we talk about, represent that, and then do the fusion. So for now, let's just continue with the intuition that I have this as input, two vectors, and I'm trying to fuse them. And by the way, when you learn a fusion module, there's nothing that stops you to jointly train the encoder, and that's something really interesting and important. Like, although I say, hey, it's a little bit simpler, but there's really going to be two problems here. One is take this and bring it to a space where that space is very related to that other space in such a way that the fusion is possible. So the encoder, the unimodal encoder, has a big job to be done as well. Now, you could just pre-train it and not fine-tune it for the fusion, and you could just train it like a word-to-vec just on words and just get it as input. Or you could say, okay, I have word-to-vec. Maybe I add a few more layers to word-to-vec, layers of neural network to just help fine-tune a little bit my model for that specific task. So both approaches are happening. So 2 vectors, how do I fuse them? What's the simplest way to fuse them? And I'm about to share, like, in my days, in one of those moments, in my days, there were only 2 fusion approaches. There were late fusion and early fusion, and that's it. And that's it. So I will often use that term, and so I just wanted to share you how they were used 20 years ago, and we're now these days people use early and late fusion in slightly different ways, but this is how they were meant originally. So early fusion was meant as a concatenation. Take both of your modalities. At that point, if you remember, there was no concept of taking raw modalities as input. We never did that. What we did is we engineered features. We talked about these engineered features, and we also had vectors for each representation. They were nicely engineered. And so each modality had a vector. And so early fusion was just a concatenation. And then any model you wanted to do the prediction task. Early and late fusion were 95% of the time used in supervised learning tasks. Self-supervised, the term didn't exist. Unsupervised existed, but this was often more about clustering. So we go with one.
Well, there's a cabling issue
Okay.
that's been persistent. If you'd like to use the wireless, that will work on both. Or we can do HDMI with one.
We'll continue.
Okay.
Sorry for
Yeah.
that.
Oh, no, I'm
Yeah.
sorry for the
Okay.
issue.
Okay, thank you. Sorry for your neck, everybody on this side. So prediction, and then late fusion was the idea that you bring each modality a prediction. So the models were really, each modality had a model, and then you had some way to aggregate those predictions. It could be majority vote, it could be an average, or sometimes you will have another model just taking these 2 values and train just on that fusion. But at each modality were there. So yeah, okay, that's interesting. So that's great. Yeah. So reasoning, when I use the term reasoning often, I imply that as I'm making my decision, I'm going to have intermediate steps, intermediate stages of reasoning, inference steps of reasoning. And often these intermediate steps will be somewhat human interpretable, or as human interpretable as possible. I mean, not all reasoning has, but usually reasoning has intermediate steps. So your observation in that sense, yes, there's more reasoning in that version than there is here, because yes, this is directly black box, no intermediate stage. While here, I have those intermediate stages for each modality, then I can just aggregate or find a way to bring it. So yeah, there's a little bit more reasoning. I mean, I think of reasoning as not like, it's not just like there is some and there's none, it's more of a spectrum. So here the reasoning is a lot more opaque, while here it's a lot more human interpretable. Now, what I would call a full reasoning will have a lot more stages than 2 stages of reasoning. Often we'll have a lot of those intermediate stages. Yeah, and that's why I'm introducing those terms, but they don't have a perfect mapping to the previous slide. So those terms were 20 years ago always used. There was no terminology of representation learning. It came in 2006, this terminology, and this whole concept that features will not be like engineered but learned from scratch had been explored, but not at the level that we have now. So the equivalent to what we do. So a lot of time you will say we do end up concatenating, and you could call this concatenation an early fusion, but often this concatenation will, let's say, will happen at that moment. So do you really call this an early fusion? It's not really an early fusion. Yes, it's a concatenation. Like I have an encoder, and then at that point I will concatenate them. But that terminology of early versus late, I just wanted to acknowledge it. But in the world of representation learning, let's just call it concatenation. Let's just call it early fusion in that sense. So yes, that terminology, people will still use it, but just be careful. It makes a lot of sense when you're not in representation learning world and you're really predicting, and it's a model prediction. But in representation learning world, let's just call it concatenation. And this, you could say it's an ensemble of model, like it's an ensemble of model ensemble of experts. Yeah. What I'm about to, let me give you the punch. It's an additive fusion you do for one layer neural network. It's additive fusion. There's no interaction between the elements other than adding. You're just adding, yes. If you have multiple layer neural network, then you're doing more than additive. But a one layer neural network fusion is an additive fusion. Really good. Okay, just to, I have it in a later slide. Oh, anyway, yeah, you have it in a later slide, exactly this. So yeah, good. So let me now talk about basic fusion. How do I bring these two modalities together? And I want to do the fusion. So the goal is to model the cross-modal interaction. And I love to always come back to statistics because there's a lot to learn from really understanding your data and really understanding interactions. So I'm going to take more multidimensional and I'm going to bring it. So univariate, just a fancy word for one dimension. Okay. So I'm going from multidimension to one dimension. And the reason for that is linear regression. This is a great invention. And linear regression, if you understand it well, you can do a lot with this. And there's probably more paper, not maybe no more, but a lot of paper or scientific, let's call them scientific papers using linear regression. So I just want to study this mostly because it does give us a basis to do fusion afterward. So linear regression has really an intercept. We'll talk about it, a bias term, has this really interesting term. So we don't always think, because what is it that I cannot model? Everything that is not able to model is left in this error or residual. So what it is let's say I'm going to do fusion, but I know that this very simple fusion of doing just additive or multiplicative is not going to be sufficient. I know that the fusion is probably doing more than just additive and first order multiplicative, but I will say, hey, it's okay. Put everything you cannot model in that other term and keep it there. So the first part is the additive, how each modality by itself is a good predictor. And here we have it as a representation, but it could be a label for now, a label Y. And then you have the multiplicative term, like the interaction term, how they're really interacting. So linear regression is used for, I don't know, let's call it real research, but for scientific knowledge discovery and testing, research hypothesis. And I know you're not in this class for the purpose of research hypothesis testing, but I will give you 3 slides on that topic because I think it's important and it will give you some good intuition for later as well. So what's really nice with linear regression is that if you have a data set, and this one is a multimodal data set of YouTube book reviews, and you want to know if the audience trusts the person speaking. So that's your why, like, and you want to know what makes someone trustworthy or appearance of trust or knowledgeable or like, I like that review. And one could be question about like percentage of smile. LP smiles all the time, so you must be trustworthy. Or maybe not. And then you're like, oh, but there's this other variable, which is that person an official critic or an amateur, like someone who's not officially a critic? And I would like to test some real research hypotheses. So I would say, hey, does smiling reveal what the audience score is? That's a simple hypothesis. The second one, does the effect of smiling depend on professional status? So does the effect of smiling on the audience score depend on the status? So let's do the first one because that's the easiest. But before we do that, I want to explain every parameter but the beauty of linear regression is that you get a population and then you choose some nice simple system of equation. Like you write one equation like this for each of your data points. So you get a system of equation like this, and then you just optimize to get the optimal parameters. And what's really nice is once you optimize and find those parameters, these parameters tell you a lot about the data and they allow you to answer questions. So the W0 tells you how, in general, like independent of smiling or not, how people are trusting the videos or not. Like, are they liking all of them? Because there kind of is a bias. You always want to be a nice person when you score others. So you're not going to give everybody a 0 right away. Like everybody is kind of a 4 at least out of 7. Like you're not going to be. So it's kind of a normal kind of bias that happens. The W1 and W2 will give you the effect of smiling. And here's the beauty here is W1 tells you how much smiling by itself, like it's only because of the smiling, not because of the other variable or the interaction. So the linear regression, when it optimizes, it tries to find the parameters that says, hey, this is only because of smiling, this is only because of professional status, or this is only because of the interaction. So you can really decouple the effect of each variable with the linear regression approach. And finally, the residual is whatever is not an additive or multiplicative. Anything that is beyond these two. Maybe there's a second order term or something nonlinear that is. So to predict the first one, I will do the simplest of linear regression. I will just try to predict. And so what does W0 and W1 in this case? So W1 is the slope, okay? And W0 is my intercept with the y-axis. So the W0 is the intercept, and the W1 is my axis. Here's the one thing you may or may not do often, but you should also think about is confidence intervals. And there's many different ways of measuring, like statistical, but confidence interval is one. And it's relatively easy to compute. So let's say I have all this data, and I randomly sample maybe 60% of my data, and I I optimize my model for 60% of my data and get a W0 and a W1. And then I randomly sample another 60%. I get another W0 and another W1, and I do 1,000 times, let's say. Then I will get some estimate. I mean, there's different ways of computing that, but this gives you a range of 95% of the time, like confidence, 95% confident that the parameter is within this interval. So if you see this interval, then the rule of thumb is that if this interval does not have 0 in it, then there is an effect. There's really like this slope is always positive. It never goes negative. So you can say, now there are other tests you could do. You could do a t-test or p-test to get some different p-values from that to test your hypothesis. But one nice way is this confidence interval. So this confidence interval can tell you, yes, there is. Smiling does have an impact on the audience score. Now, I could go and say, but what about professional status? And I could do it not the wrong way, but the simple way, which is just adding it and say, hey, one and the other, and just put them together. What do I get? I get W1. W1 gives me that slope here. W2, because it's a 0-1 kind of feature, is just like this change. W2 is this change that gives me that other. Now, if this one was continuous, it would be hard to plot this in 2D. It would be a 3D plot because it would be XA, XB, and you will have the Y. So it would be kind of a 3D plot that you will have to plot. So you can again plot the estimates, the intercept, the slope without, this is the slopes without, and you see the value change. The value change because now this is what's only the smiling that is not related to the professional status. That's what this one is. And finally, you can learn, yes, there's a positive effect and there's a negative effect from there. It's always, it never crosses 0 here. And the final one is the product one. And that's the beauty, like that's really cool because now W1 is this one. Is like when XB is 0, these two terms, if non-critic, these two terms are 0, that's it. But what's really interesting is now, because when the XB is 1, now you have this shift, but this is the slope, the extra slope. This is the extra slope in a sense. This is the change on the slope caused by the interaction. That's what the W3 is. So the W3 really gives you the interaction of the different modalities. And so this tells you that, yes, there was an effect of smiling. And I really thought originally this number was much, much higher originally, if you remember, if I just do it by itself. But if I look more carefully, the smiling by itself is not the main factor. It's depending on the professional status, it has a much bigger impact. So it is that's what you get from this, yeah. Yeah, and the way to do it is like, so if you're a critic, you lose, like by default being a critic, people don't like you a lot. But if you're a critic and you smile, then that's good. Like so a non-critic doesn't need to smile as much to be liked, but a critic needs to smile more to be liked. That's at least that's the interpretation of this data. It's interesting. So and you just answered this by those 3 numbers. And now you've done real science in that sense. Okay, so now let's use this approach, so linear regression with additive and multiplicative term. And so you have additive term, you have multiplicative. In the statistic, they don't use it. You don't use the term multiplicative. They just call it the interaction term, because usually most models have only two inputs, two features. So there's either additive or interaction terms. But they're usually what you want is to have both of them together. So we take this, which was done in univariate, and now we're going to go back to the multivariate, okay? The goal is to take the intuition from statistics and see how can we do multimodal fusion with our vectors. And the simplest, what is the simplest fusion you can do? Oh, concatenation will be one, but additive is the simplest one based on what we just described. Is like, so really what it does is just it's kind of a mixture of experts kind of thing. You're like you're taking like both modalities and saying, I'm just going to add them together to give me my representation. So this is the simplest, and it's a very healthy one to try. I'm going to show you results later on it, but very healthy one to use. And that was the punchline you gave me. So a one-layer neural network, if you think about it, mathematically, forget the activation function for a second, but the way it is done, it is adding things together. So a one-layer neural network is mostly additive. It doesn't have multiplicative terms in it, second-order multiplicative terms. And so many unimodal encoders, if you do a one-layer neural network after the unimodal, you really what you have is additive fusion, a one-layer neural network. Yeah, and you could call it a late fusion, or it was a question of like an ensemble kind of. That's kind of an ensemble or mixture of experts that you have. Now you would like to multiply. So one approach is to just multiply both, and that would be the simple multiplicative fusion. The problem here is if you have two vectors, let's say you learn Word2Vec and you learn a CNN representation separately. Now, there's nothing when you learn Word2Vec that said the first dimension of Word2Vec should have any kind of link with the first dimension of the CNN. Like they were trained separately. So there's no like mapping between that. So unless you fine-tune your representations, never use simple multiplicative one, because this only works if both spaces have been, in a sense, some kind of aligned where each dimension have a meaningful equivalence to the other one. That's the same for the additive. You cannot do additive unless your two spaces, you're about to add them, like say, dimension by dimension, only can do that if you before that brought your spaces in equivalent. But there is a better one, which is the bilinear fusion, where you take the two and you transpose one, and you multiply the transpose by, in that case, it's okay if they have not been aligned, because this matrix is going to try every possible permutation, every possible interaction. So bilinear fusion is if you ask me, the basic block and very efficient one is probably the bilinear fusion, because that one, unless you've really spent a lot of time bringing both of your spaces in equivalence, 1110. So bilinear fusion, but bilinear fusion will only look at the interaction. So there's been some extension to that. One of them is called tensor. Oh, sorry, yeah. If there've been homogeneous, let's say, if you were Word2Vec and CNN, and you just take them at face value. I would say additive, one layer neural network, which is kind of additive, or multiplicative. You're fighting a battle that's really hard because the dimensions are not aligned. They don't equivalent. Like first dimension of a word doesn't relate with first dimension of your CNN. So unless you have a few neural layers before you do your fusion, so you're either like Word2Vec and you add a few layers on Word2Vec to allow the model to take that representation and kind of reshuffle it in such a way that it can be added to each other. But if you just take them at face value, Word2Vec and CNN, and really just add them and multiply them, you're making it really hard to your model at that point. So what I was saying, if you're planning to do additive and multiplicative, be sure that between your representations and the fusion that you're about to do, be sure that you allow maybe a few layers of neurons to kind of reshuffle things so that the two spaces are synchronized in a sense. Yeah, that's what I meant. Okay, but the bilinear doesn't require that. But then and there's a trick that's called we call it tensor fusion, which is if you add a little one to each of your modality and do the same bilinear product, what you get is a matrix again. But that matrix is nice because it includes inside it both the unimodal and the bimodal interaction. So it's a little trick. Like by just adding the little one, you suddenly have your unimodal representation is still there and the bimodal. And you can do that for a trimodal case as well. The student who did that had a lot of fun creating that. Yeah. These representations, usually you can, there's no issue with derivative, like the gradient usually flows nicely, yeah. When I say add one, it's literally the vector, you just add another dimension and you set the number one to it. So, so from a derivative perspective, it is like you could imagine this being a cross product and then a neural network just after that. So I can maybe draw it on but there's not an issue by adding the one. It should not bring an issue with the gradient. I don't think so. Yeah. I could look at it mathematically. I'm quite sure we managed to, but I don't think there was any trick. But maybe there was a trick and I don't remember. But it is just by adding the one, it's a simple little trick. Yeah. This one would be a kind of a bias term. You could see it as a bias term for the whole as well. Yes. That's another way to see it. But if you have a matrix, like usually you're going to create your tensor. A tensor is just a fancy word for multi-dimensional matrix, by the way. So a tensor is just like a 2D matrix is a tensor. A 3D matrix is a tensor. There's some nice work in computer vision also on tensors, but for now, just think of tensor as a matrix. So then you will multiply this usually by a W matrix. But if you have multiple kernels or multiple layers, so this can get, especially in this case, the W matrix can get really big. So there was a nice little trick that was offered, which is, hey, this big W matrix that needs to be applied on that tensor, it's getting quite computationally extensive, especially if you have 4 or 5 modalities. So is there a way to decompose this in such a way that you decompose the W, you will decompose the Z, and you're going to rearrange them in such a way that it becomes more like linear in that sense. So here's really cool animations of one of my students, previous student. So the W matrix, what you will do is suppose that this matrix can be decomposed with a series of simpler matrices that are multiplied with each other. The Z, originally, we created the tensor, but you could also, the Z, simply keep the original two vectors. And then here's the beauty of the animation. You can rearrange all this. You can rearrange, and mathematically, this is equivalent. So I did not create the big tensor, but mathematically, it is equivalent. And so I can stack many modalities this way. Although it looks really complex, at the end, you can decompose this in a low rank representation. So instead of creating the full tensor, you in fact have some low rank. And low rank is just because if you, that big tensor you could also take an approximation of it and not keep all different bases of it and keep only a subset of them if you know that the variance is over a subset, like 95% of the variance, as you would do in a PCA, for example. So this is tensor. So, and I want to go even more so this is, let's try to go even more complex fusion, but still interpretable. Because I don't want to go all the way to the black box, nonlinear, multi-layer of neural network yet. I know it's going to happen at some point, but for now, the fusion, I try to keep it as interpretable as possible. So we look at additive fusion, one layer neural network. We look at additive and multiplicative together. And if you think about it, this is a first order polynomial. Here you have a term that makes it a second order polynomial. And here the trimodal fusion, there is the unimodal terms that are first order. There is the bimodal terms that are second order because there's a multiplication of two terms. And then there's the trimodal terms that bring the third order. But then I could ask you, what if I want even higher order interaction terms? Maybe I want this kind of, where it's the square of A, the square of B times the square of C. Like, I want to explore different ways and see if this weight is really necessary or not, or really are these only necessary. And this was a nice paper, Nurit's paper, I think. What it did is like they took both modalities and also appended the one to it, two modalities. So if you have two modalities, and then they just multiplied that vector over and over and over. So in the tensor fusion, you just multiplied once, but there's nothing that stops you from multiplying that vector, multiply it over and over. And you always multiply by its transpose, but yeah, you keep multiplying. So you multiply a vector by its transpose, you get a matrix. And then from that matrix multiplied by the transpose, you get a cube. And then this multiplied by this, you get a 4D matrix. And then you go again and you get a 5D matrix. And that 5D matrix is going to include all possible permutation, all possible first, second, third, fourth, and fifth order terms. And because of that same low rank tensor approximation, it turned out that you can do all of it without really creating the 5D tensor. That was the cool part of it. So you're able to study all these 5 different order without really creating a 5-order matrix. And that was the beauty of that paper. So this is one part of the fusion, a big part of the fusion, additive, multiplicative, and tensor and polynomial fusion. Now, the second part, we're like gated fusion. Gated fusion is another very popular one where you are bringing one modality and you have both modalities and you're going to use a gate. And I'm going to explain in a second, but for now, the gate will give me some kind of weight. to weight the modality, and it's kind of weighted fusion. That's another way we could call it. Gated fusion is weighted fusion. And then once I weighted each modality, then I can fuse them. I could fuse them with additive, multiplicative, or any kind of fusion I would like to. And to decide the weight of each modality, I could do it in a self-gating way where the modality looks and decides itself if it is how it should be weighted, kind of looking at how confident, like maybe it looks at the image and say, oh, how much noise is in the image? And because there's a lot of noise, I'm going to dynamically decide that I'm weighting myself down. Or you could also use the other modality as an input to that gate to kind of compare, hey, language looks more promising for this sample than this image. And so I'm going to relatively weight them each other. So the magic here is that, let's say I have additive fusion here, is that I will have this gate. And this gate can be seen like, you may have heard the attention fusion or attention modules. And I mentioned here that I have an output that is a vector, the same size as the modalities, but you could also do it where the output is one number, like that just tell me one modality, how do I trust it? That is also part of gated fusion. And so the gate, what is the gate? So you can call it a gate. It's kind of the negative way of thinking about it, which is a neural network designed to mask unwanted signal. Or you could be an optimistic or more positive and say, the gate is a neural network designed to select preferable signal. And that's kind of attention module. So, but attention module, gate module, they're the same, okay? So a gate, attention is just a new term for a gate that has been very popularized originally in machine translation. And then image captioning, and now is part of transformers very much. So a gate takes an input, I on purpose put it ambiguous, and then do some processing to get some kind of attention weight or gating weight. And there is at least two categories or two families of attention or gate. One is the soft attention, which is 98% of the gates that are there are soft attention. And mostly because if it's a soft math or soft number between 0 and 1, then it usually can compute the derivative of it easily in the gradient. But then there are a few cases where you can do hard gating. Really, I'm selecting one or the other. Usually it comes often with reinforcement learning or something similar to that. So hard gating, this is really nice, but a little bit more computationally challenging. So what should be the input of the gate is kind of a science in itself. Yeah. Oh, max pooling is, max pooling is, you can see it as a gate. It is taking your input. The difference here. Good. Took me a second. Is that in the pooling, you take your data, you go through the pooling function, and you get an output. The gate is slightly different, where you get your data. You go through the gate, and that data will be multiplied again by your input data. So the general concept of pooling and max pooling is kind of a hard attention way, but the gate versus a pooling are slightly different, because the pooling is really kind of a direct transformation of the data, while the other has kind of that intermediate result that is then multiplying with the input. So slightly different than that, but the general idea is the same. So the question is like, what should be the input of that gate? Should be the target that will be applied to these weights, or another modality? Often people just use all modality, any kind of information you have that could help with that decision. So now that you have this concept of gate, you can do some very interesting things. So one of them is called shifting fusion. shifting fusion. So because up to now, we always said that all my modalities are all equivalent. Modality, they're all kind of the same, and I'm trying to fuse them. But what if I have one modality that I know is my primary modality? That's the one I really believe in. And the other ones are just there to help. They're not there. Then what you can do is use a gate kind of to learn a shift that will be added to my primary modality. So my primary modality is the one I trust. And I'm going to learn a way to shift it in such a way that I get my shifted representation. And so I forgot who asked that question earlier, but modulation. Someone asked about modulation. So that's an example of modulation in a sense. So primary modality may be language, and then acoustic and visual. And so you may have like the word expectation. That's the original representation of it. And then the acoustic could shift it. Sometimes it may be shifted negatively because negative expression, or maybe sometimes it's shifted positively because of positive expression. So that's an example of modulation. There's another one which I like very much also, is dynamic fusion. So now we've studied so many different ways that fusion could happen. We said, hey, we could add it, we could multiply it, we can do unimodal, we can do bimodal and all this. What if I try all of them, almost like kitchen sink, try all of them and let the model weight each of these approaches. And that weighting could, and then you do the fusion from that, and that weighting could be soft or hard. So the soft will just be nice because it's easy to implement, and I can implement it easy. The hard attention will probably require reinforcement learning to select. And so the hard version is sometimes called architecture search. So I'm going to search different ways to do the fusion, and I'm going to select a subset of it to be the one I use. So that's really nice. So fusion to architecture search. And finally, the nonlinear fusion, the bounding box, the black box version of it, where I bring all my modalities together in my black box. I don't really know what happened. I have many layers of neural network, and I do fusion, and I get better performance on my downstream path. So I must be doing something good. So let me get my NeurIPS. For people who got it yesterday at 7 p.m. So nonlinear fusion is a very valid approach. You take all your input, put it through multiple layers, and get your output. And you could see it almost as an early fusion or concatenation. You concatenate and run it through the network. And this is the last thing I'm going to share today, is that although these nonlinear, they may sometimes end up being just additive fusion. And that's what I want to show you, the last result. It's a really nice paper that says, hey, I have this really fancy algorithm, I got better performance, but I would like to know that fancy algorithm can it be approximated with a simple additive fusion? Could there be under the hood really just two unimodal encoder and additive? And so there is this really nice paper from Yam and LP that said, yeah, let's try. Let's take this very fancy LX merge or any kind of fancy algorithm you have there, and let me try to find if I can approximate it by an additive. And that's what I will present to you right now, is that the approximation is, it says, let's take this, I train it. You train your model, you're really happy with it, that's your model. Now, what I will do is I will compute three terms with your model. The first one is I will take this model and it's called computing the expectation over one modality. What does it mean? Is I run it and I kind of do the summation in my training data over one modality. So I remove the impact of modality B. So I remove the impact of modality B. On my fancy algorithm, I remove the impact by integrating over the modality B. I remove its effect, and I only keep the effect of modality A. And I'm going to do the same for modality B. I'm going to integrate over modality A, which really just a summation over the training data of all the sample of modality A. I just integrate over, I remove that impact. And then I also can do it for both. Integrate over A and B and see what's left. This is my real multiplicative cross-modal interaction. That is the holy grail. But if I have only these two, that means there's something wrong, or at least I'm not doing as cool multimodal fusion as I thought I was doing. So the paper really, it takes this and transform it into these two unimodal terms. And then they did, and that's the last slide for today. And then they compare like 4 really cool multimodal. I mean, I don't know if SVM is a cool one, but yeah. But they take neural network as a fusion, SVM and LXMERT, and try all of these algorithms on 7 different data sets for fusion. And then they did 2 things. One is just a healthy thing. Always add a simple additive model as a baseline. It was in none of the papers that LXMERT and all this, but it's a healthy thing to have an additive, and the performance are not that bad already. And then they took the best model that exists, they copied the best model that exists, and then they created the approximation. And if these numbers are really close to each other, there's a good chance that the fancy thing that these are doing are in fact just additive fusion. That there's a really good chance that it's just additive fusion. So just the take home from that, I'm going to skip this the autoencoder part just to finally say that there's a lot of different multimodal fusion approaches that are there. And what we will talk about next week are coordination and fission, going more than just fusion from that. So thank you very much for your attention.